Hexadecimal is base 16. Apply the rule we established earlier and you immediately hit a problem. In any base n, the digits run from 0 up to n minus 1. So base 16 needs 16 distinct digit symbols running from 0 all the way to 15. But we only have 10 digit characters to work with, 0 through 9. We are 6 symbols short. The solution is simply to borrow the first 6 letters of the alphabet. A stands for 10, B for 11, C for 12, D for 13, E for 14, and F for 15. And I want to be precise about what that means, because it is where a lot of confusion starts. Those letters are not labels stuck onto numbers. In this system, they are digits in exactly the same way that 7 is a digit. The hexadecimal value F is a single digit occupying a single column, and its value is 15. Here is the full mapping, and it is worth being genuinely fluent with it rather than counting on your fingers each time. 0 through 9 map to themselves. Then 10 is A, 11 is B, 12 is C, 13 is D, 14 is E, 15 is F. A small trick that helps: F is the largest single hex digit, and it is 15, which in binary is 1111, 4 bits all switched on. If you remember that F equals 15 equals all 4 bits on, you can usually reconstruct the rest of the table quickly. The other one worth memorizing outright is A equals 10, because that is where the letters start, and it is the boundary people forget under pressure. So why does hexadecimal exist? Not because computers use it. I said this in the first video, and it is worth repeating because examiners see it answered wrongly constantly. A computer works in binary and only in binary. Hexadecimal exists purely for humans. And the reason it is base 16 specifically, rather than base 10 or any other base, is the crucial part. 16 is 2 to the power 4. That means one hexadecimal digit corresponds to exactly 4 binary digits, with nothing left over and no arithmetic required. 4 bits is called a nibble, which is half a byte. So one hex digit is 1 nibble, and 1 byte is always exactly 2 hex digits. That clean, exact relationship is the entire reason hexadecimal is the base programmers reach for. Let us convert a byte to hexadecimal. Take 11010110. The first move is always the same. Split the byte down the middle into 2 nibbles of 4 bits each. That gives us 1101 and 0110. Now convert each nibble on its own, using the place values 8, 4, 2, 1. First nibble, 1101. 8 is on, 4 is on, 2 is off, 1 is on. 8 plus 4 plus 1 is 13. 13 is not a single digit in denary, so we need a letter. 13 is D. Second nibble, 0110. 8 is off, 4 is on, 2 is on, 1 is off. 4 plus 2 is 6. 6 is below 10, so it stays as 6. Put the two together in order, and the answer is D6. That is the whole method, and notice we never once dealt with a number larger than 15. Going the other way is even easier, because you simply reverse it. Each hex digit expands into exactly 4 bits. So to turn hex into binary, take each digit one at a time and write out its 4-bit pattern. Nothing carries between them, nothing interacts. The one thing you must not do is drop leading zeros inside a nibble. If a hex digit works out to 6, that is 0110, not 110, writing 3 bits instead of 4 shifts every bit after it and corrupts the whole answer. Each hex digit contributes 4 bits, always, even when the first ones are zeros. Converting hexadecimal straight to denary uses exactly the same positional logic as every other base. The columns are powers of 16. For a 2-digit hex number, the right-hand column is 16 to the power 0, which is 1, and the left-hand column is 16 to the power 1, which is 16. Let us convert to F. Start with the right-hand column. F is 15 and it sits in the ones column, so that contributes 15 times 1, which is 15. Now the left-hand column, the digit is 2 and it sits in the 16s column, so that is 2 times 16, which is 32. Add them together, 32 plus 15 is 47, so hexadecimal 2F is 47 in denary. The method is identical to reading 3407 in denary, only the base has changed. The syllabus asks where hexadecimal is used, so let us be concrete because vague answers lose marks here. MAC addresses are written in hex, 6 pairs of hex digits identifying a piece of network hardware, and each pair is 1 byte. Color codes in web pages are hex, hash FF5733 is 3 pairs, 1 each for red, green, and blue, and each pair covers 0 to 255. Memory addresses are shown in hex because a long binary address becomes short and readable. You will also see hex in error and debugging codes and in assembly language listings. When a question asks for uses of hexadecimal, name specific ones like these rather than saying it is used in computers. Finally, the pitfall this lesson exists to kill. Because 3F looks so much shorter than 00111111, students conclude that hexadecimal saves storage space. It does not. Both of those are the same 8 bits inside the machine. Hexadecimal is a notation for humans reading and writing values. It changes nothing about how the data is stored. So if an exam question asks for the benefits of hexadecimal, the marks are for it being shorter to write, easier to read, less error-prone to copy, and mapping cleanly to binary in groups of 4. The marks are not for saving memory because that is simply false. Say that hex is compact to write and you are right. Say that hex uses less storage and you have lost the mark.